Hello everyone and welcome to part 2 of lecture 13 and 14. In the previous part, we talked about basic fundamental introduction of fire heaters. We also discussed some of the ways we can classify these fire heaters, and then we saw direct fire heaters and indirect fire heaters, and we talked about some of the features of these particular designs. In today's lecture, or in this part, we are going to talk about mainly around construction and how we can classify or so in today's part, we are going to mainly talk about different aspects of construction. Okay, so when we are talking about construction, we will look at different body types. For example, if you have a box furnace or a cylindrical furnace, what kind of tube orientation that you have inside the furnace, if the tubes are running in vertical or are the tubes are in horizontal. And then we will also look at if the furnace has a convective section, because in some furnaces we might decide to not to use convective section for some design reasons. And then finally we look at what are split burners and how we can actually use this split burners to divide different sections of a furnace. So as I said that for body type, we can have either cylindrical or box type construction. So first image shows a cylindrical arrangement where you have essentially a very large pipe, diameter pipe, and where the tubes are arranged uh, in the vicinity of the wall, and in the middle essentially you have an empty space for the flame. Okay, and then you have the image 2 and image 3. Those are box type furnaces. So you can have square arrangements or rectangular arrangements, so depending on the process and the space available. And these box type furnaces are really huge. As you can see that they are almost 2 to 3 or 4 stories high. And these furnaces are mostly used when you have very high process heating demands. Okay, so to supply high heating duties to your process. In case of cylindrical furnaces, mostly we use them for smaller processes where we don't have very huge heat duties. But because we have a cylindrical system, so you can imagine that you will have a much more uniform distribution of heat. Okay, while for the case of box type furnaces, because we have square or rectangular arrangement, so there might be some sections that are getting more heat from the flame compared to other sections. So it means that the heat distribution would not be uniform in box and in box type furnaces. So then there might be a question that why then we are using these furnaces compared to a much more uniform distribution of heat in cylindrical furnaces. So the reason we are using box furnaces is because we can get high heat duties out of them, and because if we require very high heat duty, then we have no option to use box type furnaces. But another factor, another important factor is in terms of the construction of these furnaces. So, for example, for the case of box type furnaces, a lot of these parts or sheets can be brought separately to the plant site, and then you can build this enormous structure at the site. You can weld them or join them in different ways. So you can build this whole structure on site. As such, you don't have to move this enormous structure from one place to another. Okay. While for the case of cylindrical furnace, because it is a cylindrical system, so they are not in parts. So you have to bring this whole unit as one. And as you can imagine that the logistics of this, moving this whole thing from one place to another place, or from the construction site to the plant site, it will be a nightmare, because you have to close the roads, you have to worry about the weight limits of the bridges and all these things. So that is why we, in some cases, prefer to use these kind of furnaces, because they are much more easy to construct. Okay. And then we have the second important factor, that is the tube orientation. And as the name suggests, that we have either horizontal tubes or vertical tubes present in a furnace. In the radiant section, here you can see on the in the image on the left, you have vertical rows in the radiant section, while on the image on the right, you have horizontal tubes in the radiant section. For the case of vertical furnace or vertical tubes orientation, we have a limitation in terms of the height and the structure stability. Okay, because if you have vertical tubes, then the vertical tube height is limited by the height of this overall structure. Okay, because we have to think about in terms of the stability of the structure from the civil engineering point of view, like how this furnace is going to stand, and if it is going to move because of the wind speed and wind thrust. So we have to be careful with the height of these vertical furnaces. So sometimes in plants, you might see that there are wires. Actually, they use wires to keep the structure still in high wind areas. Right? And from manufacturing point of view, these furnaces are in the range of 20 to 25 feet. So that is in American units, and in SI units it will be 6 to 7 meters high. So that is the limit in terms of manufacturing, because these furnaces come with standard sizes from the manufacturer. So this is the limit for vertical furnaces, while for the case of horizontal furnaces, we don't have such limit. We can make them as big as we want. Obviously, we still have to worry about the stability of the structure, but the length of the tube or the size of the tube is not limited by the size of this whole structure. Okay, and the reason why we use vertical tubes compared to horizontal tubes. So as you can imagine, or you might have discussed in your heat transfer courses, that when you have vertical tubes, you can use the gravity effect much more efficiently. So for example, the water will be at the bottom, and then if you are using flame to make steam or heat, it will actually evaporate and moves towards the top. Okay, so there is no clogging effect because of the fluid or the gravity of the fluid. While if you are in a horizontal tube, you have a tube filled with water or with the process fluid, and you are heating, and the vapors are being generated in the tube. So you might have a situation where you are actually have a clogging effect, where the vapors are, or the fluid is trapping the vapors, and as such you can have heat, for example, hot zones developed in the tubes. Okay, that can cause melting of the tubes as well. So here we have another view of a box type furnace, where you have this whole structure is your furnace, and then you have the radiant section that is towards at the bottom of this furnace. Then you have the convective section, and then you have the stack where the flue gases goes at the end, and then you vent it out into the atmosphere. And here you can see a cut-off version, where you have, again, you can see this is the radiant section, and that is mostly empty, because you can see there is space in between the tubes, so there is nothing here, just the flames. And then you have the convective section at the top to extract heat before you release the flue gases to the environment. And at the bottom you have these burners that are burning the fuel. And the color difference between these two tubes, you can see that these tubes are red to show that they are extremely hot compared to the tubes that are at the top. It means that the main heat or the main heating of this furnace will be done in the radiant section, and then you extract heat, the remaining heat, from the flue gas in the convective section. And then we have the case of fire heaters, where we look at that if we have a convective section or not. And a vast majority of fire heaters have convective section, and the reason, because we want to extract as much heat as possible from the flue gas before we vent it to the stack. Okay, so here we have a typical box furnace, where we have the flames at the bottom, and then you have the radiant section, where you extract heat from the flue gas using radiation mechanism, and then the flue gas passes through the convective section, where you use again these tubes or rows of tubes to extract heat from the flue gas and give it to the process streams. And finally, when we are done with our heating requirement, we release it to the stack. Okay. You might be in a situation where you are using actually a furnace that does not have a convective section, and these furnaces are mostly used for small heat duties, and because they do not have a convective section, and it means that we are not able to extract the maximum possible heat from the flue gases, and as such these furnaces are low efficiency. Okay, it means that we are going to lose quite a significant part of heat in the flue gases that we are going to vent out of the stack. So the question is then why we will use these kind of furnaces. And the reason is that we have to, when we are talking about extracting heat from the flue gas in convective section, we have to look at the amount of heat that we can extract compared to the capital cost of the piping or the tubing that we are going to use in the convective section. Okay, so this goes back again to the capital energy trade-off, and now we are looking at the energy that we are going to or the cost of energy that we are going to save in terms of extracting heat from the flue gas, but then we have to compare it with the capital cost of the tubing or the exchanger area that we need to put here in the convective section to extract the heat. Okay, so again, convective section design is an optimization problem where we look at the capital energy trade-off. So I'm going to talk about in terms of construction of fire heater is if we are going to split the burners, or in other words, if we are going to use multiple burners. And the reason we do that is because by splitting the burners, we can actually get a better control in terms of heat transfer or heat distribution inside the furnace. And if you remember that for the case of box furnaces, I said that there might be some dead zones because it's a very large furnace. So if you have just one burner, you might create a lot of dead zones. So by splitting the burners or by using multiple burners, we can actually get rid of these dead zones. So here, for example, you have one configuration where you are using two burners, and these two burners are separated by radiant tubes. The rest of the design is just like a typical box furnace. In the second case, you have a refractory bridge wall between the two burners, and then in the last here you have actually two different chambers. So here let's look at of these a couple of different configurations. So here we already discussed that where we have only one burner, vertical tubes, and no convective section. In the second case, we have two burners, vertical tubes, and convective section, and these two burners are working next to each other without any division between the two flames. Then we have, for example, here you have two burners divided by radiant tubes, okay? And then you have case E, that is actually where you have two burners, but they are now divided by a bridge wall. And this bridge wall is made of refractory bricks that are insulating bricks that you use to line the surface of this furnace so that it protects the casing of the furnace from the inner flame. Okay, so this gray part is actually all refractory bricks that kind of protect the casing. And now in this case here you have a middle refractory bridge wall that is actually separating the two flames, and as such you have you can say smaller chambers inside a bigger furnace. And in part F, you have actually physically divided the whole furnace into two chambers or cells, for example. And these kind of furnaces are very common in steam crackers. So as I said before, that you can use these furnaces as reactors as well. So steam cracking is a kind of a reaction system. And we have here two cells, and of course this arrangement is actually designed to maximize the heat transfer in production of olefins, for example, ethylene, propylene, and butadiene. So by dividing a bigger furnace into smaller chambers, you have a much better control of the flame and the heat transfer in this chamber. Okay, and then this chamber is operating independently of this chamber to some level. Obviously, they are connected, but you have much better control here compared to using one burner in the whole furnace. Okay, so the last thing that we are going to talk about in terms of construction of fire heaters is how we are going to provide the flow of combustion air to the fire heater. And as you can see on the slide, there are a couple of options available to us. We can use natural draft, that is the case here, where we are using the density difference between the flue gas and the incoming air to create a natural draft or a push for the air to come into the furnace. Then you can have mechanical draft. It means that you are either using a fan or a blower to force the air inside the furnace. So you can have a fan or a blower at the inlet of the furnace at the bottom, where you are forcing the air from the bottom and then burning it, and then the flue gases move towards the stack. Or you can have a situation where you are using to remove the flue gases from the furnace, and as such you are creating a negative pressure, and that actually sucks the air into the furnace. Okay, comparing the inlet fan versus the outlet fan. So the inlet blower or the fan will be much cheaper because you are just pushing air at a much lower temperature compared to the temperature of the flue gases here. And finally, you have a configuration where you are using two different fans, so one fan at the inlet of the air and one fan for the outlet flow rate of the flue gases. And by using two different fans at the inlet and outlet, you are in a better situation to regulate the flow rates of inlet air and the outlet flue gas. Okay, so these are a couple of options that we can use to supply air for the burning of our fuel. And as you know that a perfect air to fuel ratio is very important for efficient burning of our fuel. Okay, so that is all for this part. Thank you for your time.